to the second tutorial in the series on trigonometry. Now, in this important tutorial, I'm going to discuss the right-angled triangle. We're going to briefly talk about Pythagoras' theorem, and then we're going to carefully define three functions that we're going to see a lot of in the next few tutorials: the sine function, the cosine function, and the tangent function. And I will end the tutorial by just discussing some relationships between sine, cosine, and tangent. So to start with, let's just draw a right-angled triangle. Now, when we label triangles, it's often helpful to have a little bit of a sort of notation that we label the vertices by capital letters, and we label the lines by small letters that correspond to the opposing vertex. So this line here, we can say it has a length little a, and we choose a because it's opposite to this vertex, capital A. And we'll say that this line here has a length little b, and then this line here, opposite to the right angle, we'll say has a length c. And in a right angle triangle, the line opposite to the right angle has a special name. It's called the hypotenuse. Now, Pythagoras' theorem states that the square of the hypotenuse is equal to the sum of the squares of the other two sides. In other words, if we take the length a squared and add to it the length b squared, then that will equal the hypotenuse squared, c squared. That is Pythagoras' theorem for any right-angled triangle. It has to be a right-angled triangle for this to be true. There is a extension of this result for any triangle, which we'll come upon in a few tutorials' time, and that's called the cosine rule. But for now, for right-angled triangles, we have this beautiful relationship, Pythagoras' theorem. Let's just give some examples. There's a famous set of numbers that give this relationship. So if we have a triangle which is a right-angled triangle, if this length is 3 and this length is 4, then we see that the hypotenuse, let's call it c squared, will be 3 squared plus 4 squared, which is equal to 9 plus 25. I beg your pardon, I'm jumping to the conclusion there. 9 plus 16, which is equal to 25, and so we see that c will be the square root of 25 is equal to 5. So that's quite a nice right-angled triangle. You can sort of easily remember 3, 4, 5 as lengths that satisfy Pythagoras' theorem. If you're given any two lengths, you can determine the third. So for example, if we just invent a right-angled triangle, let's say that the hypotenuse is 7, and let's say, for the sake of argument, this length is 2. We can determine this length, let's call it b, because from Pythagoras' theorem, 2 squared plus this unknown length squared will be the hypotenuse squared, and we're told the hypotenuse is 7. And so we have that 4 plus b squared is equal to 49. And therefore we have that b squared is 49 minus 4, which is equal to 45. And so in that case, b will be the square root of 45. Which actually, I'm just noticing, has a factor of 9, and we can use our knowledge from surds to say that's the square root of 9 times 5, and so this would actually be 3 root 5. Nice to introduce a little bit of knowledge from another topic as we go along in this set of tutorials. So you'll see that surds often appear when you're dealing with Pythagoras' theorem and right-angled triangles because of this relationship here. It's quite unusual for all the lengths to be integers. This is a beautiful but rather unusual example. So that's Pythagoras' theorem. I'm not going to prove it here, but if you go onto Wikipedia, you'll find many different proofs of Pythagoras' theorem, and it's really quite a nice topic to do some research by yourselves to see the many different ways that you can prove and motivate Pythagoras' theorem. For our purposes, though, it's more important to press on and talk about these definitions of sine, cosine, and tangent. So let me use this same triangle because it's a reasonably drawn triangle, and let's consider this angle. I'm going to call the angle A, and let's define the following. I want to define the sine of A, and we abbreviate the word sine, which is S-I-N-E, we abbreviate it to S-I-N when we talk about the function sine. The sine of A is defined to be the opposite side divided by the hypotenuse. And so in this triangle, the opposite side is A, and it would be little a divided by c. So that ratio of the opposite side to the hypotenuse we define to be the sine of the angle A. We define the cosine, which we abbreviate to cos of A, to be the adjacent side divided by the hypotenuse. And so the adjacent side here is the side next to the angle, which is not the hypotenuse, so that's B divided by the hypotenuse. Just a note here, I remember being confused about this when I was at school. You sometimes think, well, what's the adjacent side? Now, in an arbitrary triangle, an angle will have two adjacent sides. It will be the two sides that converge at the angle. In a right-angled triangle, for either of these two angles which are not the right angle, one of the adjacent sides is the hypotenuse. And so when we say that cos is adjacent over the hypotenuse, we are referring by adjacent to the other side that is not the hypotenuse. So this adjacent side divided by the hypotenuse, B over C. And finally, we define the tangent of A, and we abbreviate tangent to tan, and we define this to be the opposite side divided by the adjacent side, namely A over B. So very, very important definitions of sine, cosine, and tan. These are defined from a right-angled triangle, but their scope is by no means limited to right-angled triangles, and in fact we will use them throughout our study of trigonometry for triangles of any stripe. So let me box these given how important they are. Now, before we end the tutorial, I just want to point out two relationships between these functions, which I think are not often emphasized at this stage, but it's really simple to do and I think important. These functions are not independent of each other. First of all, let's use our knowledge of fractions and see what happens if we divide the sine of A by the cosine of A. Well, the sine of A is the ratio A divided by C, and we're dividing that by the cosine of A, and the cosine of A is B over C. So we have a fraction division, and we can use our knowledge of fractions to do this very simply. Remember, we turn it into a multiplication, but we flip the second fraction. And then you see we have a common factor on the top and the bottom, which is c, which we can strike out. And we're just left with a over b. But we notice that a over b is the tan of a. So for any angle, we have a nice relationship here that the tangent of a is always given by the sine of a divided by the cosine of a. And this relationship is always true and should be remembered. So tan a is sine a over cosine a. So if you know the sine and the cosine of an angle, you automatically know the tangent because it's just the ratio of sine over cosine. Now, let's look at another relationship. Let's look at the sine of a all squared plus the cosine of a all squared. Well, the sine of a is a over c, and I want to square that, and I want to add to it the square of the cosine of a. Well, a over c times a over c, using fraction multiplication, will just be a squared over c squared, and then b over c times itself will just be b squared over c squared. And now I want to add two fractions together. Notice they already have the same denominator, so I can just put the two numerators together, added together on the top, divided by the common denominator of c squared. And now look, let's invoke Pythagoras' theorem. A squared plus b squared is just the hypotenuse squared. And so we have c squared divided by c squared, which is 1. So we have discovered from Pythagoras' theorem a very beautiful result, that the square of the sine plus the square of the cosine is always equal to 1. Now, we don't write this kind of messy form here to write the square of the sine or the square of cosine, because it comes up so often. We have a little bit of a shorthand for this, and we write it as sine squared of a plus the cosine squared of a equals to 1. It's rather a horrible notation, really, but it's historically, set in stone now. This means the sine of a all squared, and this means the cosine of a all squared. And what we've shown is that the sine of a squared plus the cosine of a squared is 1. Another very important and very, very useful relationship. What this relationship tells you is that if you know the sine of an angle, you automatically know the cosine of the angle from this relationship. So in fact, there's only one independent quantity in these three definitions. For example, if we know sine, we can determine cosine from this relationship, and then once we know sine and cosine, we can divide them and get tan. So 3 definitions, but only one independent quantity. If you know any one of these, you can get the other 2. So that's fine. So a quick introduction to Pythagoras' theorem, important definitions of sine, cosine and tangent from a right-angled triangle, and then simple derivations of 2 very important relationships, tangent being sine over cosine, and then this very important and useful relationship connecting sine squared and cosine squared. In the next tutorial, in fact in the next 3 tutorials, I'm going to be applying this sort of knowledge to a set of problems. So we're going to look at determining the area of triangles, and then we're going to talk about 2 rules, the sine rule and the cosine rule, which enable you to calculate the angles and lengths in arbitrary triangles. So I hope this has been helpful, and I'll see you next time.